All right, so what's a one-parameter group? One-parameter groups play an important role in the theory of Lie groups. In particular, matrix groups, they're one of those fundamental building blocks we can use to understand the structure of a Lie group, so we should get used to them. We'll use them a little bit here in what follows. So here's the definition. A one-parameter group is simply a differentiable group homomorphism from the positive reals to the Lie group. And what that means is simply that gamma of t1 plus t2 is equal to gamma of t1 times gamma of t2. So here we have addition in the reals, and here we have matrix multiplication inside the matrix Lie group. So thankfully, we were just talking about the matrix exponential, and that's going to give us these one-parameter groups. But just, again, to smell the roses here briefly, algebraically, gamma is a homomorphism. Geometrically, gamma is a differentiable path. All right, so here's the proposition. How do you get your hands on these one-parameter groups? Well, simple, with the matrix exponential child's play, right? So for each a in GL and K, you just look at the exponentiation of a with parameter t, and that e to the ta it's a one-parameter group, all right? Conversely, every one-parameter group in GL and K has the description e to the ta for some a in GL and K. This is actually a very beautiful bit of the more abstract Lie group theory. This turns out to be true even when you're not in the matrix context. There's a way of defining exponentials on Lie groups that are not formed by matrices, that are defined by more abstract group multiplication, which is smooth. But anyway, that's a little bit beyond what we're doing. I remember it from when I had a course in it. It was really, really cool. And the one-parameter groups still play a large and important role in the general theory. But it's important to understand matrix Lie groups because they are the fundamental example of Lie groups, and they often arise in physics, as Tapp makes a powerful point of at the start of his book. He gives you a really nice list of examples there of how these come up. So anyway, the proof. Clearly, t maps to e to the ta as differentiable path, and we just proved that this is in GL and K, right? It's invertible for each a and for each ta, and for each ta really. How about the homomorphism property? Well, that's just the usual property of the matrix exponential because ta, t1a, and t2a commutes with t1 plus t2 times a. Anyway, these are commutative with respect to one another, so you get the usual exponential law. You don't have to go to that Baker-Campbell-Hausdorff stuff like we'll talk about later for more interesting non-commutative matrices. But anyway, so there you have it, the homomorphism property. And conversely, if you have a one-parameter group, suppose A is equal to gamma prime of 0, following Tapp, as we usually do. Gamma prime of t, well, we can define that in terms of the difference quotient, use the homomorphism property to pull out the gamma of t here. And then, of course, this is the derivative at 0, right, which is a. So we get gamma prime of t is equal to gamma of ta. But, hey, we already have a solution to this differential equation. We know it is e to the ta, right? And then, just to drive the point home, you can look at the gamma of t times e to the minus ta. And if you look at this derivative of this product by the product rule, oops, am I off the page? I'm off the page, aren't I? So, sorry, I'll get back on the page. So you look at, I think actually the fact that it satisfies the same differential equation and has gamma of 0 is equal to I, just like e to the ta has I. I think that suffices really to show it's the solution, but he's just driving the point home. So if you look at the product rule, you get this, but then remember this differentiates out to a and the minus from the minus ta, and so that is 0, which means that this is a constant. But if you look at time 0, this gives you that the constant is the identity matrix, and hence gamma of t is e to the ta. All right. Another important identity, which I might prove later, I forget. Anyway, it's fun to prove, is that the exponential of a similarity transformation is the similarity transformation of the exponential. So coordinate change is very kind to the matrix exponential in that sense, right? So like a BA inverse would be like a change of basis if B represents some mapping from, say, Kn to Kn. Anyway, so there's another identity which we will make use of in good time. And that brings us to chapter 7. So I'm going to, again, stop and start again.